Consider this example where we have data of some countries like Canada, China, India, Russia, and you see that we've got some values of GDP, some of GDP per capita, and human development, life expectancy, poverty, and mean income. What we are trying to get from all of these is the livability or habitability of that place. We want to see that if suppose we were immigrating to some different country, how good it would be, how suitable it is to our needs. Now, all of these values, there are one thing to note that not only there are a lot of values over here, but also the fact that some of these are much bigger than others. Okay, so we see something like 0.68, something like 73 right in there. Then we've got fractions as well. So these are basically different values, and yet they all contribute to give me the same information. So feature extraction says that we need to change these into some different format or some different representation, different dimensions, where they do give out useful information, but they are some processed version of the original ones. And all of these are like 6 different values. These can be changed into only 2 values, and these 2 values convey almost the same amount of information that we were previously extracting from 6 of these. So that's the target over here, that we get a higher dimension and we change it into a lower dimension and we get nearly the same amount of information. The trade-off is some information for a lot of complexity. So that's the overall objective, or that's what we are trying to achieve here. So let's have a look at it in a little more detail. Consider this. So like I just said, PCA is the transformation of n-dimensional data to new n dimensions, where the new dimension with the most variance is the first principal component. The next principal component or the second principal component is the one with the next most amount of variance, and so on and so forth. So if this was the original distribution of data, on the x1 axis, this is what it would look like, and on the x2 axis, this is what it would look like. It would be transformed based on its own variance. ठीक है, हम इसको इस तरह से शिफ्ट कर देंगे कि जो इसकी मोस्ट वेरिएंस वाला है वो हमारी नई प्राइमरी डिमेंशन बन जाएगी और ये दूसरी हमारी सेकेंडरी डिमेंशन बन जाएगी. And these would be given new names or new numerals, and this would be called, let's suppose, Z1, and this would be called Z2. First example, you've got 2 different scales, X1 and X2, and we've got some data points that are plotted both with regards to X1 and X2. Okay, so we see some variation regard X1 and some variation regard X2. The objective of principal component analysis, or finding different principal components, is to find the new dimensions so that they are optimized corresponding to the spread of data. So I find a new dimension over here, Z1, I call it Z1, that captures the most spread of data in this dimension. Okay? So that first line fits so that it has the minimum distance in this space. And the second principal component that we find is perpendicular to the first one. Okay? We make sure that it's perpendicular, just as we have different dimensions or dimensions in other systems, such as Euclidean systems as well, where these are perpendicular. So we find the second component perpendicular to the first one, and if we were to find third, fourth, and fifth components, they would again be perpendicular to one another. So technically, principal components are a series of linear least square fits to a sample, each orthogonal to the previous one. So the correct mathematical definition of these is that each principal component analysis is the best fit to your data, where each one of new principal component is perpendicular to the previous one. Here is what these look like. The first component captures the maximum spread or maximum variation of data. The second component captures the next maximum, and the third component captures the next one, and so on and so forth.